Welcome to the lecture number 58 of fuzzy sets, logic and systems and applications. And here we'll continue our discussion on the Larsen fuzzy model for multiple rules with multiple antecedents. And this also we'll discuss with max-min composition and max product composition for fuzzy and crisp inputs both. So since this class is having the multiple rules and multiple antecedents, so we are taking two rules here for simplicity, but we can have multiple rules, like n number of rules we can have, and similarly we can have multiple antecedents. So here also we are taking two antecedents only. So two antecedents and two rules we are taking for simplicity. So rule number 1 and rule number 2. But if we understand this, then we can apply this for multiple antecedents and multiple uh, um, rules. Means we can apply to any number of uh, rules and any number of antecedents. So here we are taking only two rules, and let us go to the first case where we are taking the fuzzy input. So we have this as the rule number 1 and this as the rule number 2. These two are the rules already uh, given for the fuzzy model, Larsen fuzzy model, and this dotted one is the applied input. So we may not at the moment consider when we are discussing the rule. Now this is the input, this is the fuzzy input, is the fuzzy input that we supply to the Larsen fuzzy model, and we have this fuzzy input for x, this fuzzy input for y. Means the fuzzy input, the fuzzy value a dash, that means the a dash is nothing but a fuzzy set here, and b dash is also a fuzzy set. So these two fuzzy values are applied, fuzzy values are given as the input to the model. So when we do that, we see that for the first rule, let us understand that when we apply this, so we superimpose a1 and a dash. So we superimpose a1 and a dash, we get the point of intersection as 0.86, and similarly here for y input we superimpose b dash and b1 was already there, and b dash is the given fuzzy input. So when we superimpose these two, or we superimpose b1 on superimpose b dash on b1, and we see that there is an intersection here, point of intersection, and this point of intersection is 0.36. So we have 2 points of intersection. First is for the x, first antecedent, and the second one is for the second antecedent. I can call this as W1 and I can call this as the W2. Now, since here we are taking max min composition, so we'll take the min of these two weights, W1 and W2. So when we take the min, and since this is for the first rule, where there are multiple rules here, means two rules, so we write the symbol of weight like this. So upper subscript here is for rules, so first rule. Similarly here the upper subscript will be the W1. So W1 basically I can, okay, so let's have this, have it like this. This symbol is a bit we can take here in this particular case, we can take this as the W1 and W12. So the lower subscript is for the rule, and so the W1 here is the W1 is equal to the minimum of the two. So W1 is equal to the minimum of W1 1 and W1 2. So this way we have the min of the two as W1. W1 is 0.36, and this we use to scale down the output fuzzy set C1. So we can very easily get this value, the C1. So this is the fuzzy output here. This is the fuzzy output. This is C1 dash, and this is nothing but mu C dash and then Z by Z. And what is mu C dash? Z is mu C dash Z is nothing but mu, but W into this is mu C dash 1. So mu C 1 dash 1 is mu C 1 dash is equal to mu C is equal to W1 into mu C1 Z. So this is how we get this value of C1 dash. Similarly, we find the points of intersection here for the second rule. We call this as the W21, and then we call this as the W22. So W2 here is equal to the min of W21, W2. So this way we get W2 here, and similarly here we get the C dash 2. So this is the fuzzy set, and this is nothing but C. This is WC2 dash Z by Z, and and mu CZ dash mu C2 dash Z is nothing but W into mu C1 dash C2 dash mu C2 Z. So this is how we get the output fuzzy set scaled. Now, since here we have multiple rules, so we have to, when we apply max min composition, so now the max is relevant here. Max of max min composition is relevant. So we have multiple rules. Here we have two rules. So both the outputs are now included. Both the outputs are now accounted, and this accounting is done by taking the union of the two. So we take the union of the two, and that's how we are getting this as the output. So this is the union of C C1 dash and C2 dash. So we can write it like this. C dash and then C2 dash. And this is our final output in this case. So now this output is the fuzzy output, and as I've already mentioned that when we are interested in crisp equivalent of this, crisp value of this, then we use suitable defuzzification methods, and we get the crisp value, the corresponding fuzzy set. Now let us compare this output of Larsen fuzzy model with the Mamdani fuzzy model. So this means that when we have for the same inputs, for the same fuzzy inputs, if we would have used Mamdani model, what we would have gotten is here. So for the same max min composition and for the same fuzzy input, we are getting the different outputs. So Mamdani model is giving us here this output, this fuzzy output, whereas the Larsen fuzzy model is giving this output. So please look at the outputs, and these two are different outputs. Now let us go ahead and use the other composition. Let us go ahead and use the max product composition. So when we use max product composition, so since we have already this as the W11 and this we have W12, so our W1 is the min of W11 and W12. So we are getting here, no, this is the product, this is not the minimum, so this is the product. What is this? This is this, we have W1 and this is we have W12. So when we multiply this, the value W1, that is the firing rule strength, is coming out to be 0.31, and we use this value to scale down the height of the C1, the fuzzy set C1 to 0.31. So this is how it is done. Now the new membership function of C1 dash, the new membership function, the scale down membership function mu C1 dash will be found using the W1 multiplied by mu C1 Z, and then we can write the C1 here, we can write the C1 dash C1, the output, the scale down fuzzy set here, mu C1 dash. Alright, so now similarly, when we apply the second rule, when we apply the input, the fuzzy inputs to the second rule, this was the rule number 1, the first rule, and then we have the second rule. Now when we apply this W2, this is the second rule, so we write W21 and then we write here W2 2. So this is W2 1, this is W2 2. Similarly, here also we have the value that we are getting as the firing strength of the rule as 0.2. So this value will be used to scale down the C2 to C2 dash. So the membership function here of this scale down fuzzy set will be mu C dash Z W 2 into mu C 2 Z, and the C2 Z C2 dash will be Z mu C2 dash, like this. So this is how we get the C2 dash as the output, the fuzzy output. Now, since we are applying here the max product composition, so we take the union of the two outputs. So we take the C1 dash, C1 dash, take C1 dash and C2 dash. So we take the union of these two, and this is what we are getting here as the output. So we see that we are finally getting the fuzzy output, and this fuzzy output can be defuzzified further to get the crisp output, and this is the output that we obtained using Larsen fuzzy model, using the third case of the Larsen fuzzy model, that is multiple rules and multiple antecedents, and this output is with respect to max product composition with fuzzy inputs. So now let us compare this case with this output with the Mamdani fuzzy model. So had it been a Mamdani fuzzy model, we would have gotten this output for the same input, for the same composition, that means the max product composition. So see here that we are getting different fuzzy outputs for the same inputs and for the same compositions. So we see clearly that we have different fuzzy outputs, and since we have the different fuzzy outputs, obviously we are going to get the different crisp values as well. Now let us compare this with the max min composition, and we see that all four are different. When we use max min composition, here also the Larsen and Mamdani both are producing different fuzzy outputs. So we can see that as to how when we use the same, even if the same max min composition, different models are producing corresponding to the same fuzzy inputs different fuzzy outputs, and so the crisp outputs also will be different. Now instead of fuzzy inputs, let us use crisp inputs and see what happens. So we have the, again for this case also we have two rules, and the input here is different, that means x is equal to x1 instead of the fuzzy set, and here we have y is equal to y1, that means the crisp input instead of the fuzzy input. So let's see what we are going to get when we apply this crisp input. So here we have, let's assume that x1 is 7 and y1 is 6.5. So when we take this x1 for the first antecedent, so first antecedent is x is a1. So when we take x1 is equal to 7, so corresponding to x1 is equal to 7, we see that this is cutting, this is intersecting the a1 fuzzy set at 0.28 membership value. So this we call as W11 for the first antecedent and first rule. This is rule number 1. This is rule number 2. So similarly here y1 is cutting, y1 is also intersecting here at 0.97. So we call this as W12, the second antecedent and first rule. So if we use max min composition, then we have to take the min of these two. So W1 is equal to, or we can simply write here like this, that we have this as the W11 and this as the W12. So the value, the minimum value is coming out to be 0.28. So since we are taking maximum composition, so the minimum here is 0.28. Now we use this value to scale down C1 to C1 dash, means the new fuzzy set is, the scale down fuzzy set is C1 dash. And as I've already discussed as to how we are going to get the membership function of the scale down, C1 dash fuzzy set. So here C1 dash will be like this, W1 multiplied by mu C1 Z, here also we'll have Z, mu C1 dash Z, and then here we'll have W1 into mu C1 Z. So with this we'll be getting mu C1 dash Z, the membership function of the scale down fuzzy set, and this scale down fuzzy set is C1 dash, and C1 dash is this mu C1 dash Z oblique Z. So similarly, when we apply the same input, same crisp inputs to the rule number 2, so here we get my W21 0.14 and W22 as 0.99. So since we are taking the max min composition, so minimum of the two will be 0.14. And similarly, here also the membership function of the scale down fuzzy set will be mu C2 dash mu C2 dash. So I can write here mu C2 dash is going to be W2 multiplied by mu C2 Z. Since this is defined in Z, so we can write here mu C2 dash Z. So like that. And then we have this C2 dash as mu C2 dash Z oblique Z. So this is how we get the expression for C2 dash. Now, since we are using here the max min composition, so the outputs corresponding to rule number 1 and rule number 2 are unionized, means the union of the two outputs are taken. So C1 dash union C2 dash, and this is what is the output that we get when we take union. We combine these two, so either we call this as the union or we take the max. So this is nothing but the union of the two outputs corresponding to the rule number 1 and rule number 2. Now let us, so since this is a fuzzy output, now let us compare this fuzzy output of the Larsen fuzzy model with the Mamdani fuzzy model with the same maximum composition and with the same crisp input. So we see that the outputs again here will differ. So Larsen fuzzy model produces this fuzzy output, whereas the Mamdani produces the different fuzzy output compared to Larsen fuzzy model. So similarly, when we defuzzify this, the crisp outputs also will remain different. So let us now, for the same input and in the same class, that means the multiple rules with multiple antecedents, let us use the max product composition and let's see what we are getting. So here we are again, for the same input, we are getting W11 as 0.28 as the point of intersection. Here we are getting W2, W11, so W12 here as the point of intersection here. So this part remains the same. The only thing is this multiplication here, because we are using max product composition, so we multiply these two, the W11 and then W12. This is W12. So final value, that is W1, is coming out to be 0.27, which is the firing strength of the rule 1. And again, it is needless to mention as to how we get the C1 dash here. So what is done here is that the height of C1 is brought down to, or is brought down to C1 dash, and the accordingly the whole fuzzy set is scaled down, and this membership function of this fuzzy set C1 dash, that means mu C1 dash Z, will get by just multiplying W1 with mu C1 Z. So when we have this, then we can simply write the expression for fuzzy set C1 dash, and C1 dash is mu C1 dash Z and then Z. So this is how we write C1 dash fuzzy set. Similarly, when we apply this crisp input, x1 is equal to 7, y1 is equal to 6.5 to the second rule, the output is C2 dash, and here this intersection is W21 and this intersection is W22. So this is our W1, this is our W21 and this is our W21, W22, W22. Similarly, the membership function of the C2 dash, so membership function of C2 dash is going to be W2 multiplied by mu C2 membership function of C2 Z. So this C2Z, this C2 dash will be nothing but Z mu C2 dash Z oblique Z. So this is how we can get the membership value and the fuzzy set. So both the outcomes are now maximized. The outcomes, that union of the two fuzzy sets are taken. So here we take the max of C1 dash and C2 dash. And this is same as the C1 C dash is equal to C1 union C2 here, and this is the outcome. So this is the fuzzy outcome, and we use the defuzzification methods, suitable defuzzification methods to get the crisp output. Now let us compare this output of the Larsen fuzzy model here, and let's compare this with Mamdani. So had it been the same input, same crisp inputs, same set of fuzzy rules and same composition, that means max product composition. So see here, the Larsen fuzzy model is giving this output, and Mamdani fuzzy model is giving this output, which is different from the Larsen fuzzy model for the same crisp inputs and same max product composition. And now let us compare the outputs of the max product composition with max min composition as well. So we see that here, all the four outcomes are different, means the fuzzy values are changing. The output of the Larsen fuzzy model in all the cases, in both the compositions are different for the same input and same composition and same input. And similarly here, the Mamdani fuzzy model also, we have different outputs. And similarly, since we have the fuzzy values are different, so the corresponding crisp values are also going to be different. So we see that we have the outputs, fuzzy outputs, in as the result of Larsen fuzzy model with crisp input and maximum composition, and then the same for max-min composition, and we see that the results are, the fuzzy outputs are different. The outputs are different, and then accordingly we can say that the crisp values are also going to be different. Now let us take a simple example, a very simple example here of the case, a single input and single output Larsen fuzzy model. So here we have the single input, it means we have the single antecedent. But here we have multiple rules. We have single antecedent but multiple rules. And in this case, we have the single input, single output, that means the CISO Larsen fuzzy model, and which is shown here for antecedent and consequent membership functions with the universe of discourse, x belonging from minus 10 to 10 and y from 0 to 10 respectively for every x belonging into capital X for every y belonging into capital Y. So we see here that the x is having three fuzzy regions: small, medium, large, and all these fuzzy regions are defined by or represented by the corresponding fuzzy sets for small, for medium, for large. Similarly, in consequent part, that means the output is also divided into y is also divided into three fuzzy regions, and every region is represented by a fuzzy value, fuzzy set. So small, medium, large. So we have the input and we have the output. And here we have the three rules of the model which is given. So rule 1 says if x is small, then y is going to be in the small. Means if any input x which is falling in the small region, then the output has to fall in the small region only. Similarly, what rule 2 is saying is if x is medium, means x is going to be medium, then y is also going to be in the medium. Means what does this mean exactly is if any input x is falling in the medium region, then y will also be falling in the medium region. Similarly, for rule 3, if x is large, means if the x values, if the input x is falling into large region, large fuzzy set region, then the corresponding y will also fall in the large region. So this is a very simple case to make you understand. So if we have these three rules present for this fuzzy model, for this CISO fuzzy model, for this CISO Larsen fuzzy model, then let us find the output corresponding to the input x is equal to minus 3.9. So let us apply this input. So please understand that the input here is the input that we are giving to the model is a crisp input. So we have x is equal to minus 3.9 and this is a crisp input. So this input when we supply to the Larsen fuzzy model, let's see what is the output that we are going to get corresponding to this input. So when we apply this input, we see that corresponding to x is equal to minus 3.9, we get here the 2 points of intersection. So we see that a small region is cut at one place, a small region, a small fuzzy set is intersected at one place by x is equal to minus 3.9 line, and similarly the medium is also intersected at point 7. And then when it comes to large is not at all affected. So the input that we are supplying here, which is x is equal to minus 3.9, is applicable, is falling into two regions, small and medium. It is not falling in the large region. So large fuzzy region is irrelevant for this input. So let us now further understand that corresponding to this input, we are getting zero point 0.3 as the point of intersection in small region and 0.7 in medium region. Now, let us check this in the given rules. So let us now look at the rules and see whether the rules are applicable for this input or not. So we have the input x is equal to minus 3.9, which is falling in the small region. So if it is falling in the small region, we have the given rule. Please see here. And in given rule, if our input is falling in the small region, so we have the output also in the small region. So this means that the input, since our input x is equal to minus 3.9 is falling in the small region, so this means rule 1 is applicable no matter what is the output. So we will first see the input. So input is falling in the small region. Then we see the input is also falling in the medium region. So rule 1 and rule 2 are applicable. And rule 3 is not applicable because the x is equal to minus 3.9 is not falling in the large region. So this rule is not applicable. So only two rules are applicable. Now let us proceed with these two rules. So we have the small fuzzy set here, the fuzzy set for small here, and then we have the fuzzy set for medium here. This is medium, this is small medium fuzzy set, and this is small fuzzy set, and these two are given. So since we have two rules here, rule number 1, let us now apply the input. So for rule number 1, and then we have the rule number 2. So when we apply the input here, we find here for the first rule we are getting the point of intersection as the weight, which is 0.3. Now if we apply Larsen fuzzy model, so the height of this output fuzzy set, that is small here in this case, we have to bring it down to the 0.3 value here. So, and the membership function, the new membership function, let's say the membership function of the small here, let's say this is y, and the membership function of the small dash, let's say, will be the w, that means the 0.3 into mu small y. So similarly here, when we apply rule number 2, we get here the point of intersection as W2, and we scale down the height of the medium to W2, that means the W2 is equal to 0.7, and this is the outcome that we get, the scale down fuzzy set and the corresponding membership function. So let's call this as the dash, medium dash. So this is y. So mu medium, so this will be basically the 0.7 mu 0.7 into mu medium dash and then y. And here we have the membership function mu medium, let's say y, and this is dash. So this is how we are getting the scale down fuzzy set. And this is the membership function. This is the membership function. We can get the fuzzy set, a small fuzzy set defined like this: y mu small dash y. Similarly here, the fuzzy set, and so this will be the fuzzy set basically. This is the fuzzy set, and here this fuzzy set here, the mu medium, this is fuzzy set, I can write it here. This fuzzy set is the, let's say, medium medium dash, and this medium dash will be like this: mu y, then mu medium dash y, and then y. So that is how we get the scale down membership function and the corresponding fuzzy set for medium dash, the scale down medium dash, scale down fuzzy set. So the same is shown here. Now, since we are using max min composition, so this is for max min composition here, this is for max min composition. So we use max min composition. So minimum we have already taken here. The minimum was not applicable because we have only one antecedent. So max min composition or max product composition, both will give the same result because we have only one antecedent here. So that is not really going to make any difference. So I can simply remove this because this is applicable to both min and max min and max product composition. But finally, in both the cases, we have to take the max of the two output. So both the output, and what is this output? This is a small dash here. This is a small dash, and this is medium dash as the fuzzy output. As the fuzzy output. So both these outputs are now taken as the union. So I can write here as the small dash union medium dash. So this is what is the output. So this is finally again the fuzzy output. Now we can use any suitable methods of defuzzification to get the crisp value. So here this is the output and fuzzy output, and when we use the centroid of area, the defuzzification gives the y star as the crisp value. So y star is 3.5420. The formula I have already discussed, all these defuzzification I have already discussed. So if we use all these, we'll get the center of area. If we use center of area, the same fuzzy value, the same fuzzy quantity is giving us different crisp values. So when we use center of area method of defuzzification, we get 3.5420. When we use the bisector of area, we get 3.6286 as the crisp value. When we use max of mean of maximum, we get 3.7287 as the crisp value. When we use the smallest of maximum, then we get 2.4625 as the crisp value, and then when we use the largest of maximum here, we get the 4.995 as the crisp value for the same fuzzy output. And here it is shown, the fuzzy output that we have got is shown, and the vertices also, all these vertices P1, P2, P3, P4, P5, P6 are shown here. If you are interested, you can use these vertices to compute and compare the and match the results that we have obtained. So we have discussed in today's lecture so many things, and I hope you enjoyed the lecture. In detail, I have discussed the Larsen fuzzy model using max-min composition and max product composition for both the inputs fuzzy and crisp. And all these three cases we have discussed when we have the Larsen fuzzy model with single rule, with single antecedent. And then this was the first case. The second case was that we discussed was single rule with multiple antecedents, and the third case that we discussed for Larsen fuzzy model was the multiple rules with multiple antecedents. And this covered almost all the cases that we could apply. And with this, I will stop here. And in the next lecture, we will discuss the Shukamoto fuzzy model. Thank you very much.